Congratulations! We have made it to the point where we are ready to graduate from two-dimensional space and curves in the plane and begin looking at curves in three-dimensional space, or curves in R3. So I want to begin just with a quick video introducing and orienting us towards three-dimensional space. And as in R2, our primary object in R3 will be the vector, and vectors in R3 will be ordered triples of numbers, x, y, z, instead of just ordered pairs of numbers, x, y. So R3 itself is going to be the set of all ordered triples, and that's the set of all real numbers, x, y, z, in which the order that we write these matter. Each of these objects in and of themselves is considered a vector, right? And we will draw these vectors and orient these vectors in three-dimensional space, much like we oriented our ordered pairs in two-dimensional space. So for example, here I've drawn a set of axes, and these are going to be our sort of x, y, z axes in three-dimensional space. Right away, it becomes a little bit more complicated, and we run into a small problem. We are used to drawing our x, y axes, but how do we orient these in three-dimensional space? In particular, every drawing that I make will be on this board, right? This is a two-dimensional board. So how do I display accurately, or at least mostly accurately, how do I display three-dimensional space on this? Well, I have to use a little bit of perspective, and I have to imagine one of these arrows, this one down here, as coming out of the board itself. So this is the arrow that's pointing out of the board and into this third dimension. Now, the way that I orient these can really be in any number of ways, but we want to follow a certain rule of orientation, and this is going to be called the right-hand rule. So the right-hand rule will tell us, if I'm labeling these axes as x, y, z, which order or which direction is the positive z direction based on the positive x and positive y direction. So specifically, let me first of all label this picture in its standard form, and that is with x coming out of the board, so this would be the x-axis, y going off to the side, and z going straight up. This is sort of the standard way to draw this. And this satisfies this so-called right-hand rule, in which I will orient this according to my right hand in such a way that I point my entire arm in the direction of the positive x direction, so that's coming out of the board or towards the camera. My fingers will curl in the direction of the positive y, so if I'm going to curl them, they'll be curled in this direction, that's the positive y direction. And if I do that with my arm in the positive x, my fingers curled in the positive y, then whatever direction my right hand thumb is pointing in will be my positive z direction. So with x and y labeled thusly, this has to be the positive z direction, according to this right-hand rule. However, there might be times when we're interested in reorienting our XYZ3 space or labeling it differently, so we can still do that, provided that we follow this right-hand rule. So let's say, for example, that I wanted to label this as my positive x direction and this is my positive y direction. Well, according to the right-hand rule, I would stick my arm in the positive x direction, my fingers would curl in the positive y direction, and in this case, my positive z direction will actually be pointing backwards into the board as opposed to coming out of the board. So probably the slightly better way to draw this would be to have that arrow sort of keep going backward and label that as the positive z direction. And here I'm just labeling the x, y, and z in the direction of their positive orientation. So that helps keep me organized if I were to, for example, rotate three-dimensional space. I would keep in mind what orientation I'm under. Now, with those orientations determined thusly, I suppose, any vector that we want can now be drawn in three-dimensional space. And just like before, we'll have several equivalent definitions, right? So for example, one thing that I might do is I might describe the vector, let's say the vector 1, 0, 1. Right? The vector 1, 0, 1, that will be the vector with 1 in the x direction, 0 in the y direction, and 1 in the z direction. I could also equivalently label that using my column vector notation, so 1, 0, 1. Both of those are totally fine. And I want to equivalently, like before, interpret this, either or as a point in three-dimensional space or as a arrow going from the origin to that point, right? And I can interpret this depending on the situation. So in this case, 1, 0, 1, I would have to go 1 unit out in the x direction. Let me try that again. 1 unit out in the x direction, right? So maybe this is out to 1. 0 in the y direction, and then 1 unit up in the z direction. And so this would be the point 1, 0, 1, or equivalently, I could draw my vector like that. Okay, and I could similarly draw this vector in this picture under that proper orientation by going in the x direction 1 unit, 0 in the y, and then 1 in the z direction. And so I would get that as my equivalent vector, just from this different perspective. Okay, so with that in mind, we're treating vectors, we're writing them like this or like this. Many things are the same. There are a few new wrinkles that will get added, and we'll see them as we go. The first is that I want to define several special vectors in three-dimensional space. All right, and these are going to be my named vectors I, j, and k, so named. These will be the vectors of unit length that point in the sort of cardinal directions, right? So just in the x direction, just in the y, just in the z. And specifically, my vector I will be the vector that points just in the x direction, that's 1, 0, 0. J points just in the y direction, 0, 1, 0. K just points straight up, 0, 0, 1. And so these are my named vectors because these are in some sense very fundamental vectors in three-dimensional space. And in particular, the set of these three taken together, right, so I, j, and k taken together, form what is called an orthonormal basis for R3. Now, what do I mean by this? This is language that will appear in linear algebra, but orthonormal basis, right? Unpacking each of the parts of this word, ortho meaning orthogonal. All three of these vectors are orthogonal to each other. They meet in 90 degrees, right? So they're all 90 degrees apart from each other. They're all perpendicular to each other. They're all orthogonal to each other. Normal in the sense that they're all normalized. They all have length equal to 1, right? So each of these meets in a perpendicular direction from each other. They each have unit length, and taken together, there are 3 of them, and they can be used to describe any point in R3. So they form what's called a basis for R3. And all I mean by basis is that every point in R3 can be uniquely described using the vectors I, j, and k. So for example, if I took a vector, let's take the vector 1, 2, 8, right? I can rewrite this using my I, j, and k vectors. And specifically, this vector is the vector that's equal to 1i plus 2j plus 8k. And so when I say that we have a basis for R3, that I, j, and k form a basis, what I mean is that I can write this vector using those I, j, and k vectors. And I can do this in a unique way. Again, that is more the domain of linear algebra, but I want to introduce that language here, the orthonormal basis I, j, and k. All right, love it. All right. With that in mind, we can now turn to talk about parametrized curves in three-dimensional space. And it turns out that much of what we talked about in two-dimensional space carries over, especially the early stuff. So we'll still be using our parametrized curve. We'll use the capital X to describe it. It will be from an interval of time with parameter typically t into three-dimensional space. And we'll see an example here in a moment. With that in mind, x prime, the derivative of each of these components, will still be the velocity vector, the associated velocity vector, and the double bar of x prime, right, so the length of x prime will still represent the speed of the parameterization. Similarly, I suppose, our x prime, right, I should say our integral of the speed will still give us the total length of the curve. So we can still calculate speed, velocity, and arc length just as we had in the past. And just like in R2, we can parameterize curves by arc length. We can make it so they have unit speed parameterization is another way to say that, and so on and so on. So let's look at an example, right? And just like we started with circles last time, we're going to start with something kind of similar here. Let's look at the parameterized curve x of t equals cosine of t, comma sine of t, comma t for t values between 0 and 6 pi. And for the purposes of this example, I'm going to keep our space oriented in the usual way, with x coming out of the board. So what does this curve look like? Notice it has 3 components, so every moment in time t is describing a point in 3-dimensional space. And as we go forward in time, we're going to imagine this particle tracing out some sort of curve in 3-dimensional space. But what curve is it tracing out? Well, if we think about it, right, and if we cover up this third variable for a moment, or this third component for a moment, the x and y components here, right, this was the, this was our x of t, this was our y of t, and I guess this is, we're currently covering it up, but this is our z of t, right? Our x of t and y of t are describing the x and y components, and that's just cosine comma sine. We've seen that before. That's our circle. That's our unit circle. So what we have here is in the x, y dimensions, we're tracing out a circle, right? A unit circle moving at, in the x, y dimensions at unit speed. But what's happening over here? In the z component, right, we just have this variable t. And as t ranges from 0 up to 6 pi, our height of our curve will increase. So we're tracing out a circle, but our height, or I should say tracing out a circle in the x, y directions, but our height is just going to increase here. And so what we get is actually going to be what's called a helix. We're going to start here, and then as we trace out, we'll sort of loop around. And if we're going to 6 pi, it'll be a helix with 3 total rotations, right? So it'll go around the circle once, twice, 3 times, all the while going up in the air, and it will stop 6 pi units above where it started. To be slightly more precise, at time t equals 0, we're starting at the point 1, 0, 0, and then when we end at 6 pi, we're at cosine of 6 pi, comma sine of 6 pi, comma 6 pi. So we're up at this point right here. All right. Cool. I guess while we're at it, right, just to confirm, if we want to, we can calculate the rest of these quantities that we're used to as well. So in particular, x prime, well, that's just going to be the derivative of each of these. So that's going to be negative sine, cosine, comma 1, right? And that's going to describe our velocity vector at any given point. Our velocity vector will just be the vector that's pointing off sort of tangent to the curve at that moment in time. And notice the negative sine, comma cosine, comma 1 suggests that it's going around the circle, but increasing as it does so, right? Its z component is positive 1, so it's always pointing up a little bit, and our curve is always going up a little bit. Finally, the speed, right, will just be x of t, I should say x prime of t, with the norms, or with the length, and that would be the square root of x prime dotted with x prime. So that's going to be negative sine quantity squared, like this, plus cosine squared, plus 1 squared. Should have made that a little bit longer there. And what we'll get here, right? So we still get sine squared plus cosine squared is 1, so this becomes square root of 1 plus 1, so this is the square root of 2. So our helix is moving at a constant speed, and that constant speed is exactly square root of 2. Finally, if we wanted, we can integrate up the total length of this curve, right? And because it's a constant speed, that's pretty straightforward. So the length of the curve would be the integral from 0 to 6 pi of this speed, square root of 2. And that is just going to be 6 times square root of 2 times pi. So there we have not only this curve, but its velocity, speed, and length all computed. And as we see, it's almost identical, basically identical to what we did in the case of vectors in a plane, or curves in a plane. So coming up next time, we'll begin to see some ways in which three-dimensional space differs from two-dimensional space, and we'll see the issues inherent there as we continue this generalization into this maybe richer three-dimensional environment.